And so let's look at Coulomb's law. We've seen something very similar to Coulomb's law previously when we did the universal law of gravitation. If you remember, I'm going to write this up here on the side. Universal law of gravitation was G(m)(m) over r squared. We didn't spend long on it, but that's the force between two objects of mass. We're going to see something very similar with Coulomb's law, and that is that the force between two charges, F, is equal to K Q1 Q2 over r squared. This is on your equation sheet, and you'll have some problems on the upcoming test where you have to work with Coulomb's law, determining the force on certain charges, and we'll do some examples. Here, K is Coulomb's constant. It's equal to 9 times 10 to the 9th. Let's see, it has units of Newton meters squared per Coulomb squared. Q is in units of coulombs. That's the SI unit for charge. And R is in units in the SI unit of meters. Listen, I just want to remind you of our metric prefixes, especially ones that we're going to use a lot this semester. Oh, I think I do it on the next page. Is that right? Yeah, so remind you of these metric prefixes, that mu, the Greek letter mu is micro, and so we're going to go back to that page. I just want to remind you of these metric prefixes, that mu is micro, that's 10 to the minus 6, and n is nano, that's 10 to the minus 9, because we're going to be dealing with really small charges. Just to remind you too, you'll see these as well. Centimeter, like centi is 10 to the minus 2. Milli is 10 to the minus 3. On the big end, we'll see kilo, mega, and giga. That's 10 to the 3rd, 10 to the 6th, and 10 to the 9th. All right, so you'll see those. Now I'm going to go back to the previous page, and we'll have a big shuffle. Okay, so here, our force, our Q1 is the charge here, Q2 is the charge here. They can be different or are the same charges, it doesn't really matter. The distance R is just the distance between them. So that's this value here. This gives the magnitude of the force. We'll consider the direction of the force based on the idea that like charges attract and opposite charges repel, right? Like charges attract. No, that's not right. Like charges repel one another, right? If I have two positive charges, they fly away from one another, and a positive and a negative charge, they attract one another. All right, so we'll just use Coulomb's law to calculate the magnitude of the force. And as I said, Coulomb's law is similar in form and action. That means just the equation is similar in form, and then also how it acts. You know, that it's an inverse square law, that it's dependent upon these charges, is similar in form and action to Newton's universal law of gravitation. Any idea why that might be the case? I mean, they look very similar, those equations. Why is it that those two equations look so similar? You ever thought of that? Like, is there some connection between gravity and electricity that we just don't know about that makes those equations look fundamentally to be very, very similar? K QQ over R squared, G MM over R squared. They're what? They are field forces, right? That might be part of it, but huh? Okay, yeah. So how close the objects are, that affects the charge, because it's a one, or the force. It's a 1 over r squared dependence for both of them. Yeah, those are both true, and those are sort of part of it. But largely, the reason they're so similar is because they're both spherically symmetric forces. Right, and when we deal with these forces, we deal with spherically symmetric objects, masses, charges, what have you. All right, so they're similar in form and action because of the spherical symmetry. All right, now Newton's third law also applies, so that if we have a force on charge 1 due to charge 2, then it'll be equal and opposite. So here, I have two charges, plus Q1, plus Q2. We're just going to sort of sketch in what the forces look like. There's a force that's acting on this charge. That's in which direction? Up, down, left, right? Which is it? Now, these don't exist. This is a separate situation. Up, down, left, right? Left is right, right? And not left is correct, right? And then here, I get a force to the right, because those are two like charges that are going to repel one another. I'm going to have a force in this direction. I'm going to call that the force on particle 1 due to particle 2. And then the force in this direction, oh, it should be the same. I'm going to call it the force on particle 2 due to particle 1. Now, the magnitude of F12 is equal to the magnitude of F21. That's Newton's third law, that for every force that I have this equal and opposite force. We saw that with Newton's universal law of gravitation too, right? That the Earth pulls down on me with 700 newtons of force, and likewise, I pull back up on the Earth with 700 newtons of force. Remember that? Yeah. Now here, my forces are going to be the same in magnitude as they were above, but they'll be in different directions. So I have F12 in this direction, and I have F21 in this direction. As we're working through these problems with Coulomb's law, we'll first sketch out the forces, and then we'll determine the magnitude, and then we'll do our vector business, like we like to do. Let's do that, actually. We are going to see some more vectors. It's just going to be this chapter, I think. I don't think we see vectors after this chapter. But it's just like what we did last semester. So you got this down, but it's like one last hoorah that I get to make sure that you understand how to do vector math. So when you have more than two charges, you can determine the force on one of the charges by adding the vector forces from the other two charges. So for example, I have these three charges, and I want to know what is the net force on Q3. I have a positive 2 Coulomb charge, a negative 1 Coulomb charge, and then I have a positive 4 Coulomb charge. The first thing I want to do is just sketch in the forces as they act on this Q3. So if I'm to draw the force due to particle 2, or due to particle 1, on particle 3, I'm going to draw it like this. This is going to be F on 3 due to 1. That is the force due to this particle. They're both positive, so they're repulsive. Here, this is a negative particle, and so my force, the force on particle 3 due to particle 2, is going to be in that direction. All right, so what is the net force on Q3? Well, now our next step will be to find what is the magnitude of F31 and what is the magnitude of F32. So F32 is going to be K Q3 Q2 over R squared. That's going to be the distance between particle 3 and 2. I'll give you just a minute. K has a value of 9 times 10 to the 9th. That's 9E9 if you use the exponent button on your calculator. Q3 here is 4 coulombs. Q2 is 1 coulomb. Notice I'm leaving out the sign. I'm not really worried about the sign because I included the sign when I drew that vector. With me? What's the distance between those? Well, this is one particle. This is the other particle. They're 2 meters apart. It is an inverse square law, so that's squared. Listen, on your test, you'll see that I like to give numbers that work out easily. So you see here that I do get some things that cancel out. The 2 squared is 4, so that cancels with that. And I'm just left with F32 is 9 times 10 to the 9th newtons. Listen, a coulomb of charge That's a big charge. Usually when you have charges, you're talking about micro or nano coulombs. So you'll get used to this. We'll work through some other problems where you have to use micro or nano coulombs. Just make sure that you're up on those metric prefixes, especially the micro and the nano for this upcoming test. Micro is 10 to the what? -6. And nano sort of looks like what? 9, but -9, like nanotech is really small. Okay? And then we do the same for F31. That's going to be 9 times 10 to the 9th. That's K. That's my K value. Q3 is 4 coulombs. Q1 is 2 coulombs. And then the distance, what is the distance between Q3 and Q1? Well, here's Q3. Here's Q1. I have 1 meter. I have 2 meter. So it's 1 plus 2 are 3 meters. Want to square it. Be careful. We're going to have some equations that all look a little bit similar, okay? Like we're going to have another equation coming up where I have this exact same thing except I have r in the denominator. Just try to keep them all straight in your head. You're going to have them written down in front of you, but keep them straight in your head. Here the 3 squared cancels with that 9, and I'm left with 8 times 10 to the 9th. All right, so now if I want to know the net force, the sum of all these forces is F31 minus F32. That is 8 times 10 to the 9th minus 9 times 10 to the 9th. Newtons, which is minus 1 times 10 to the 9th. So the net force on this charge is to the left at 1 times 10 to the 9th newtons. Okay? You could see a one-dimensional problem that deals with vectors, but we'll also see a two-dimensional problem, which we'll work through one now, and you have some in your homework. You know, I always put a 2D problem, so look back at the old test too for some examples, and we'll work through some in class. So 2D problems, I want to know what is the force on Q3. So just like we did before, I'm going to label my forces on Q3. I have 2 charges. This one's positive, this one's negative, and Q3 itself is positive. So I have a force due to this charge on this charge. It's going to be left or right? It's going to be to the left, attractive, because this charge is negative, this charge is positive. These 2 charges attract one another, so the force is in that direction. So if I draw, I'm going to call that F32. And then I also have F31, which is in this direction. Okay? Now I want to know the net force on that. So in order to do that, I select my coordinate system. It's going to look like that. There's my F32. I'll need to figure out some angles. Let's go ahead and do that, okay? And I'll also need to figure out a distance. Notice that I have a triangle here. It's a right triangle. What's the hypotenuse of that triangle? All right, it's a 3, 4, 5 triangle. So this is 5 meters. Can y'all see that? Yeah. I'll need to know as well this angle on the triangle. You could find that angle, I'll call it theta, is equal to the inverse tan of, I always forget this, it's SOHCAHTOA, T tan, opposite over adjacent. The opposite side to theta here is what? It's 3. Right, so it's inverse tan of 3 over 4, and that's equal to, it's 37, I think, right? It is 37. Am I right? 37? Yeah. All right, so that angle is 37. Notice that this angle is the same. Because I have 2 lines that are crossing one another like this. Those two complement, I think they're, these 2 angles, they're the same. They have a name. Complementary? No. Is that what it's called? No. No, we have to add up 9. I don't care what you call it. But they're what? Really? I don't know. Y'all know what I was doing in geometry in high school, right? Did I tell y'all that story about my geometry teacher? Ethel. Huh? The batteries, right. What a jerk, man. Me. It was so mean. All right, this is 37 degrees. So now we want to resolve F31. Actually, no, we want to find F31 first. I'm sorry. Find F31 and F32. So F31 is K Q3 Q1 over 5 meters squared. That's the distance between them. And let's see, I'm just going to tell you what that is. I get 1.08 times 10 to the minus 9 for F31. Newtons. And then in a similar way, F32 is equal to 1.13 times 10 to the minus 9. I have plugged in K and the various values for Q. These are nanocoulombs now, so it's -9. And then I find the X and Y components. So if I'm thinking about my coordinate system, I'm going to have new vectors on it. I'm going to have F31Y, F31X, and F32 over there. I'm going to have those three vectors. I'm going to add them up and find the sum of those, the vector of sum. So do I have an extra space on the next page now? Okay, so now I find F31X and F31Y. I'm going to take this value, F31X is 1.08 times 10 to the minus 9 newtons. Let's see, for the X component, use the sine or the cosine? Gosh, this was like months ago we did this. What is it? Cosine. All right, it's the cosine of 37. And then for F31Y, that's 1.08 times 10 to the minus 9 sine of 37. Once I get those, I get the values. They are equal to, well, I don't have their values, actually. But I can add up the X components. I do the sum of the forces in the X. It is F31X minus F32. That has a value equal to negative 2.67 times 10 to the minus 10 newtons. And then I do the sum of the forces in the Y. Is just F31Y, which is 6.5 times 10 to the minus 10. All right, I know I'm going through this a little fast, but we did this a lot last semester. We're going to do it one more time when we get to fields. Okay, now I have one final step. I have the X and Y component of the final vector. What do I have to do to it? Use that old, what was that old guy that used that thing? Pythagorean theorem, right? And then also the tangent to find the angle. So to find the final force, I like to first sketch it. I have my Y component is positive, my X component is negative, so my resultant force is going to look something like this. It'll be in that second quadrant. To find the magnitude of it, I say the square root of fx squared plus fy squared. This is fx. This is fy. Putting those in, I get 7 times 10 to the minus 10, 7.03. And then to find this angle, I'll call it phi. Phi is the inverse tan of Fy over Fx, which is 67 degrees above the negative x-axis. Listen, you're not going to have a problem that has every part that this problem has in it. I'm going to show you some sample problems that you can practice, but your problems will be similar but just fewer steps. You'll just have sort of a piece of this problem to work at various points on the exam. So don't freak out. You know, like that just took him like 10 minutes to work through that. I can't do that on the exam, and you can't. So that's why I give you, you know, sort of smaller pieces of the question as we go through it on the exam. And let me show you some examples of that. Let's try this quick test first. Consider this configuration of charges. Which vector best represents the net force acting on this rightmost charge? So you should start just sketching in the vectors and then sketch them also to scale. So if one charge exerts a bigger force than the other charge, then you draw that vector bigger. And then after you draw those two vectors, ask yourself which of these vectors represents the vector sum of those two vectors that you've sketched in. All right, we'll stop in just a few seconds at 110. Let's say 110. Okay, good. There's some ambiguity in this, but I think E is the best answer. Let me show you why. Because if I draw the force between these two charges, I'm going to get a force that's about that big, roughly. However, this charge is bigger, so the force is at least going to be twice as big, and it's also closer. So this charge is going to create a force that looks like that. And then, you know, there's some argument as to whether it's D or E, but I'm fairly certain that the best answer for this is E, and that's what most of you have put. Again, I understand this question is kind of ambiguous, and on the test I'll make it less ambiguous. So that's good. Let's try this next question. We'll see some more like that soon. What is the magnitude of the force on the negative 6 nanocoulomb charge? If you can't see this, this is positive 3 up here, and this is minus 6, if you don't have it in front of you. And they're both nanocoulombs. If you finish this one, go on and figure out the direction of the force on the minus 6 nanocoulomb charge, and we'll do that next. Okay, I'm going to stop at 1. Stop at 140. 140. Just a couple more seconds. Okay, I'm pretty sure that's right. Let's just double check. We'll work through it. So here I need to know this distance. This distance is the square root of 0.5 squared plus 0.5 squared. I think that's 0.71, am I right? Yeah, it's the square root of a half. Then my force is going to be 9 times 10 to the ninth. Q, 3 times 10 to the minus 9. 6 times 10 to the minus 9. Divided by 0.71 squared, which should be a half, right? Yeah, so that's a half. Let's see, that can cancel, and 27. Yeah, I get A. 3.2 times 10 to the minus 7. Y'all concur? All right, good. Now let's try what is the direction. Sorry. What is the direction of the force on the minus 6 nanocoulomb charge? Notice it's an equilateral right triangle. It'll help you a little bit, but. All right, I'm going to stop at 50 seconds. 50. A is right. I understand why you put B, but watch the words there, because if it was B, the force would be over here. That would be 45 degrees. And the force is not in that direction. Instead, the force is attractive, and so it's going to be in that direction on the minus 6 nanocoulomb charge. And this angle, because it's an equilateral right triangle, is 45 degrees. So that's 45 degrees above the negative x-axis. And then it's like, well, that's not on there. So you got to go looking around. Realize that often we measure our angle from the positive x-axis, and 180 minus 45 is equal to 135. So A is the right answer. Good job on that one. Sort of good. You're going to see some vectors. Several questions on the next test will be related to vectors. So it's not insignificant, but it's also something that we've seen before. Just make sure that you got it for the exam. It will be there for certain. There's some questions in the homework to help you with that. We'll see some more. We're not done with vectors. When we get into fields, we'll do it again. So if you didn't get it this time, that's okay. We'll have one more chance. Okay, so one more thing, and then I'll show you the Venn diagram. The electric field exists in the space surrounding a charged object. And in fact, the electric field really just describes the force that a charged particle feels. And my wife was telling me that she calls it a force field. Those of you in her lab who have that opportunity, she calls it a force field, because that's really what it is. It just describes the force that a charge feels. And there are other fields that we use, like a gravitational field, that also describe a force. So an electric field is nothing fancy. It just helps us to describe what the force does, what force the charge feels. And we define our electric field then as a force, this is the definition of electric field, divided by Q naught, where Q naught is an imaginary positive test charge. The units of the electric field are newtons per coulomb. Later we'll see, or you might see elsewhere, I'm just going to write it here sort of as an aside, the units are also volts per meter. We'll see that again a little bit later not much, but if you see this on the MCAT or whatever, you might see electric field in units of volts per meter instead of newtons per coulomb. When a charge Q is within an electric field, the force the charge feels is F equal to Q times E. Now, listen, we'll talk more about this imaginary positive test charge. You're probably like, what the heck? Why do we need an imaginary positive test charge? The positive test charge just helps us to map out the electric field, to sort of figure out what the electric field is. It's not a real thing. It just helps us to determine the direction of the electric field. And we'll see that a little bit later. But we can also have charges that are inside an electric field. And that's what we're talking about here. When a charge is inside an electric field, it actually feels a force. Okay? We're going to get into that in a little bit, but for now I want to show you the Graaff generator, and if we have time, we'll return to this, or it might be on Monday when we come back. In just a second, plug this in. Have y'all ever seen one of these before? Yeah, some of you have. It's probably seen it on TV at least. This is called a Graaff generator, and what it does is it takes charges. I told you about my roommate, Chris. You know, like we were in a band together. Did y'all know that I was in a band? Did you? Like when I was in high school, I was in a and Chris was our lead guitarist and singer. I'll play bass. All right. So, remember I told you the story about shuffling my feet on the carpet and then zapping them on the ear? Well, what this does is it has a belt here. See the belt? It moves like this. And then when it goes down inside the base here, there's a little piece of carpet. And it continually rubs its feet on the carpet. And it picks up charges and it takes them up to this metal sphere and dumps all those charges onto that metal sphere. And so as you can imagine, this metal sphere is a whole lot of what on it? A whole bunch of electrons. Because it takes all those negative charges up on this little belt and then it dumps them onto the sphere. Are they all isolated right up here at the top, or do they spread out evenly? They spread out evenly, right? Hey, what's up? Y'all are supposed to come into the room today like all a bunch of positive charges and spread out like this with a conductor sheet of paper. But look at you, you got all these positive charges up here, all clustered, and then y'all are sort of spread out. There it is. Okay. What I have here is just a metal rod, and it's going to attach this thing to the ground. So I can turn this deal on, and then have electrons will jump from this sphere onto this sphere. All right? Want to see? Let's turn the light out. Remember, on human days, this doesn't work very well. Why is that? Right, water is polar, it strips electrons away, but it's not real human in here. I'm going to build up for a bit. There we go. That's what it looked like with Chris's ear. Can y'all see that? Now listen, it takes the energy per charge, that's voltage or potential, the voltage, which is an energy per charge, for an electron to jump about an inch across air, is about 10,000 volts. So in order to make an electron move across 1 inch of air, just regular air, requires about 10,000 volts. That's about 10,000 joules per coulomb. Right? In contrast, our electric output is 120 volts. So holding it up here, that's about 30 or 40,000 volts, because 10,000 per inch. That's 3 or 4 inches. I'm not shaking this. There's actually a force between the two spheres, because you have those charges. Hopefully it's very simple. So you can actually feel the electric charge. You've probably seen this where people their hair stands up. Have y'all seen that before? Move this up. Somebody want to do this? Put your hands on it. Who wants to? Okay, anybody? Darker hair if you can hear. Well, we'll see. I'm not sure how it'll move. So you grab that stool over there. We're gonna have to try to stand on the stool because, and then you want to move over here. You really don't want to be close to her at all. So just put the stool down there. Right, you can stand on it. And it's safe to touch. Now you can touch it. But once I start it, you don't pull your hands off until I tell you. Okay? Alright, so I'm going to turn it on. How does it feel, China? Is it tingling at all? Like I can usually feel it tingling on my arm. I can see your hair. You can take one hand off and you can swoosh through your hair a little bit. It's all pooping up on the side. You can see a reflection in the thing. Keep your hand on there. So she's getting lots of charges that are built up on her body, and they're going out to the furthest points of her body. They're trying to get off of the body and go up to the atmosphere, and that's why her hair all stands up. They're sort of getting onto her hair and they're repelling one another. I'm going to turn it off. Don't touch me while I hold it in like this, and then you can sort of step. Now you can step off, and you can just sort of. They'll go away. Anyone else want to try?
What would happen if you took both hands off before you said this?
Well, if you take both hands off, the sphere continues to build up charge, and eventually you would have charges that would jump over to you from the sphere. All right. Did you want to try it? No. Ladies with light colored hair work really well. All right. Any guys or any ladies? Asia, do you want to try it? Okay, come on. Oh, on a day like today. Ready, go. Yeah, you have wavy hair, but my daughter, she can get on there and go. If you want to take one hand and sort of swoosh your hair back, sort of the ends up. How's it feel? It's kind of right. All right, I'm going to turn it off. All right, let me show you. Anyone else want to try? All right, let me show you something. Look, I don't have much here, so Anna, can you turn it on when I have something? I don't have much here, but let me show you something.
It looks so natural.
Yeah, I used that, but it wasn't good. All of it. All right, so you can see it's starting to move a little bit. A lightning rod, allows charges to escape from your home into the atmosphere. So I have like a little lightning rod. It's just a nail. Watch when I have it covered up right now, but watch what happens when I uncover. You see my hair go down? Because it's allowing those charges to escape into the atmosphere. They all collect at this little point. And if I cover up that point, they go back up again. If I remove that point for the exit, it will cause it to go back up. Oh, you can turn it off. Alright, we're going to get into electric fields soon, but I wanted to show you something. I can map out the electric field of this thing because I have these special, like I went on this science catalog, and they have these special things. They're like called electric field mappers. And they allow you to map out the electric field. So when you turn this thing on, there's electric field lines coming all out. Like we're going to get an electric field soon. So just sort of bear with it. Some of you have already seen it in lab, but electric fields measure the force that a charge feels, and they sort of come out and go around and come back into the thing. But this will allow us to see the shape of those electric fields. There are these specialized little electric field mappers. You ever seen what's that called? Twister? Yeah, it's like the little balls that help you to track out the tornado. It's sort of like that. Oh. Oh. They're not really special. That's right. Alright. Anyway, that's a Graaff generator. I have 2 more minutes. What's that? Let's look at a couple more things. We have a few more minutes. I told you our anniversary was it yesterday or the day before? It was the 18th. We're going out tonight, so we didn't have a babysitter the other night, but we have one tonight. We're going to Sinclair. Have y'all ever been there? I've never been there. It's a little pricey for us, like we can't really afford it, but tonight we're going to afford it. Does anybody work there? Who? All right, let's try this clicker test question. Says a proton is accelerated from rest in an electric field of 100 volts per meter, or newtons per coulomb. Right, remember that's the same. What is the velocity of the proton after 2 seconds? Now, I have a couple things going on. Our electric field, or the force, electric field is 2 times E, right? The charge times the electric field, and then we also know Newton's second law. So there are several steps here. I'm going to sort of just jog your memory that we have some equations we're pulling from last semester that you'll also need to know for this semester. Our kinematics also, V equals V naught plus AT, and X equals V naught T plus 1/2 AT squared. So a couple things you'll need to do. You need to find the force, the electric force due to this field, the acceleration, and then the velocity. Look on your equation sheet. There are some constants there that you'll also need to know, or that you'll need to use regarding the proton. This is the proton, right? Yeah, regarding the proton. Oh, I've got me in a shirt for red. All right, people, let's do about 10 more seconds. I'll stop at 240. $240. Just a couple more seconds. Just guess if you don't know. Okay, let's see. What is B? All right, so first I have to find the force. Q times E. That's 1.6 times 10 to the minus 19 coulombs. That's the fundamental unit of charge, which is for a proton. The electric field is 100 volts per meter or newtons per coulomb. And so that's 1.6 times 10 to the minus 17 newtons. Then we need to find our acceleration, F over m, which is 9.6 times 10 to the ninth meters per second squared. I took the mass of a proton. Here I gave it to you, but on the test I won't give it to you. It's on your equation sheet, so you just need to be aware that it's there. And then also, I find the velocity, which is what I'm asking for. V naught is 0, and so it's just a times t, which is going to be this acceleration times this time, which is b. 1.9 times 10 to the 10. Listen, we'll see some other questions like that in the homework that are similar but different. But you need to know how to use an electric field in order to figure out how a charge moves. That's what we use electric fields for, to move charges around. We'll talk more about sort of some of the health applications for that, and then also the physical applications. Y'all have a great weekend, and I'll see you on Sunday.
I have a question about this one.